Okay, so at the previous lecture, we briefly discussed, mostly without proofs, some basics of spectral theory in Banach algebras. And to complete this survey, let's now recall the notion of a spectral radius in Banach algebras. So suppose that A is a unital Banach algebra, and little a is an element of this algebra. And we also assume that A is non-zero, of course. Then we define the spectral radius of our element to be the supremum of the following set. So for every lambda in the spectrum, we take the absolute value of lambda, and then we take the supremum over the spectrum. So the spectrum is non-empty, so this number is well defined, and moreover it is finite because the spectrum is bounded, and moreover the spectrum is compact. Let's recall from the previous lecture that for every lambda in the spectrum, the absolute value of the lambda is less than or equal to the norm of A. So as a result, we deduce that the spectral radius, that is the supremum of all such numbers, is also less than or equal to the norm of A. Sometimes, in some concrete algebras, this is actually an exact equality. For example, if we take the algebra of bounded functions, L infinity, on an arbitrary set, then it's clear that the spectral radius is exactly the norm for every element in our algebra. Well, just because the spectrum of A is the closure of the range of A. And the supremum over the set is just the supremum norm of our function. And the same holds for many other Banach algebras consisting of bounded functions. For example, for the algebra CB of X of continuous bounded functions on a topological space. Another simple but useful example where we have an exact equality between the spectral radius and the norm is a diagonal operator on a finite dimensional Hilbert space. So it is represented by a diagonal matrix with respect to a suitable orthonormal basis. And if A has this property, then the spectrum consists of all eigenvalues, that is, all the numbers lambda 1 to lambda n. So the spectral radius is the maximum of these numbers, and clearly the norm is exactly the same. So again, in this case, we have the equality. On the other hand, it's rather easy to construct a counterexample where this inequality is strict. If we take, for instance, the algebra of 2 by 2 matrices, that is the algebra of operators on the two-dimensional space, and consider the operator given by the following matrix, then, well, the matrix is upper diagonal, so the spectrum is located as the diagonal. And since we have zeros on the diagonal, the spectrum is 0. And so the spectral radius is also 0. But the norm is positive because the operator is non-trivial. And we can also easily generalize this example as follows. This is a little but useful exercise to show that if we have a nilpotent element in any unital algebra, then the spectrum of this element is 0. So the only point in the spectrum is 0. So if A is a Banach algebra, then the spectral radius of A is 0. But if A is a non-zero nilpotent element, so we see that the spectral radius is strictly less than the norm. In the general case, the spectral radius of an element in a Banach algebra is given by the following useful formula, which is traditionally attributed to Berling and Gelfand. In fact, the truth is that this theorem was actually proved by Gelfand in 1941, and Berling proved earlier this formula for a very concrete Banach algebra, which is a weighted version of L1 of Z, of the group algebra of the integers, equipped with a suitable weight. And so now such algebras are called Berling algebras. But his proof was applicable only to his concrete algebra. And Gelfand's proof is true for any commutative unital, for any unital Banach algebra. So the spectral radius of A, of any element in our algebra, is given is equal to the limit of the following sequence, or equivalently, we take the infimum of the same sequence and we get the same number. Again, I'll not give you the proof because for linear operators, this formula is normally proved in functional analysis courses. And for arbitrary Banach algebras, the proof is exactly the same. The idea is as follows. It's quite easy to show that the spectral radius is less than or equal to the infimum for the simple reason that if we take lambda in the spectrum, then lambda of n, lambda to the nth power will be in the spectrum of a to the power n by the spectral mapping formula. So the absolute value of this element is less than or equal to the norm of the same element, of this element. And then we just take the nth root and take the infimum over n. And we see that the spectral radius is less than or equal to this infimum. The opposite inequality is more interesting. Basically, here the idea is, again, it comes from complex analysis. So we take any bounded linear functional f on A and consider the following function of lambda, which is defined in a suitable disk. Actually, it is defined in the open disk centered at 0 of radius 1 over r of A. And it's rather easy to show that this function is holomorphic, so we can consider its Taylor series at 0 and calculate explicitly the Taylor coefficients. And it turns out that the Taylor coefficients are precisely f of A to the power n. And then by using some simple estimates, we deduce that, and also applying the uniform boundedness principle, the Banach-Steinhaus theorem, we deduce that this limit, or more exactly so far we don't know about the existence of the limit. So we can prove that the upper limit, lim sup, of the sequence is less than or equal to the spectral radius. And combining these two inequalities, we deduce that the limit exists and that the limit is given by this formula. So briefly, this is the idea of the proof. Here in a simple corollary, we see that the spectral radius of A is 0, if and only if this limit is 0. And what does this mean explicitly? If we write explicitly that the limit is 0 in terms of epsilon and n, we deduce that this means that for every positive epsilon, the sequence of norms of powers of A decays faster than any geometric progression in this sense. So, for example, if A to the power n behaves something like 1 over n factorial, then this sequence satisfies this condition. And such elements, by definition, such elements are called quasi-nilpotent elements. For an obvious reason, because if A is nilpotent, then this sequence is eventually 0. And quasi-nilpotent, in the quasi-nilpotent case, it is not necessarily eventually 0, but it decays to 0 very fast. And a typical example, maybe the most classical example of a quasi-nilpotent element is the so-called Volterra integral operator. It acts on the big L2 space on the interval AB. It is determined by a certain measurable function k. So let's assume that k is measurable and bounded. And we define our operator by the following formula. So it's essential then that we integrate from A to X. An important special case is the case where k is identically 1. And in this case, Vk of f is the antiderivative operator. So it's a classical exercise in functional analysis to show that this operator is quasi-nilpotent. So we can explicitly estimate the norm of the nth power of this operator and deduce that it behaves, it is dominated by a constant divided by n factorial. So it is quasi-nilpotent. Another important corollary from the Berlin-Gelfand formula is the following one. Basically, it states that the spectral radius of an element doesn't depend on the choice of a subalgebra containing this element. In other words, if we take a closed subalgebra of A, as denoted by B, which contains the identity of A, so they have a common identity, then for every element in B, the spectral radius of this element calculated with respect to B is the same as the spectral radius calculated with respect to A. By the way, let's recall that the spectra of this element with respect to A and B can be different. In the general case, the spectrum with respect to A can be smaller than the spectrum with respect to B. But the spectral radius will be the same. The spectral radius will be the same. And this is indeed clear from this formula, because this formula involves only the norms of the powers of A. And of course, this doesn't depend on whether we can consider A as an element of a big algebra or of the smaller algebra. Okay, so this completes on our picture of elementary spectral theory in Banach algebras. Our next strategic goal will be to discuss the basics of Gelfand's theory of commutative Banach algebras. I have already told you that this will be our main tool. This theory will be our main tool in proving the basic principles of commutative harmonic analysis on locally compact abelian groups. So the main ingredients of the theory of commutative Banach algebras are the maximal spectrum and the Gelfand transform. So let's start with some purely algebraic definitions. Suppose that A is a commutative unital algebra. So far, we don't assume that it's a Banach algebra. This is a pure algebraic picture. So A is just a commutative unital algebra. And suppose we have a proper ideal, I of A. And we say that this ideal is maximal if it satisfies the following condition. So if there is no ideal J which is strictly bigger than I and which is strictly contained in A. So in other words, this means that maximal ideal is just a maximal element in the set of in the ordered set of all proper ideals of A. Of course, this doesn't mean that that this is the largest ideal. In many concrete algebras, we have no largest ideal, but we have many. We can have many maximal ideals. This is a typical picture. Sometimes it is convenient to characterize maximal ideals in slightly different terms. This is a simple exercise in algebra to show that a proper ideal I of A is maximal if and only if the quotient of A modulo I is a field. Now we introduce the maximal spectrum of A. So by definition, the maximal spectrum of A is the set of all maximal ideals of A. Here is a simple example. Let's look at the polynomial algebra in one variable. Then it's a simple exercise to show that we have a one-to-one correspondence, a bijection, between the maximal spectrum of this algebra and the complex plane. Explicitly, for every point P in the complex plane, the corresponding maximal ideal MP consists of all polynomials F which vanish at P. So this is a bijection between the complex plane and the maximal spectrum. Actually, this result can be extended to the algebra of polynomials in several variables. But this is no longer an exercise. This is not trivial. Actually, this is a corollary of the famous Hilbert-Snurstein sets. But in the one variable case, this is very easy. Okay, now how about the existence of maximal ideals in the general case? Well, they do exist, and moreover, we have the following result. Each proper ideal of A is contained in a maximal ideal. So in particular, if we start with the zero ideal, then we deduce that we always have a maximal ideals. The proof is a standard application of Zorn's lemma. So we take an arbitrary proper ideal I of A, and we consider the collection, the set of all proper ideals of A, which contain I. So this set is non-empty because it contains I itself, and it's a partially ordered set for the inclusion order. And I claim that this set satisfies the conditions of Zorn's lemma. Well, indeed, why is it so? We can take any chain C, that is a totally ordered subset in M. We want to find an upper bound for C. And to find an upper bound, we simply take the union of all ideals in this chain. Well, since C is a chain, it is easily seen that K is actually an ideal. And obviously it contains I. Why is it proper? Well, our algebra is unital. By the way, it's essential here that it is unital. So each ideal J in C is proper, and so it doesn't contain the identity of A. So this obviously implies that the identity is not in K, and so K is a proper ideal. And clearly K is an upper bound, so it's an element in M, and it's an upper bound for our chain C. So we see that every chain has an upper bound, so Zorn's lemma implies that M has a maximal element. That is, we obtain a maximal ideal containing I. And this completes the proof. Let's now look at another set, which is closely related to the maximal spectrum. We define the character space of A to be the set consisting of all non-zero characters of A. So let's recall that a character is an algebra homomorphism from A to the complex numbers. And let's also recall that if A is unital, then every non-zero character is automatically unital. So it takes the identity of A to 1. We denote this set by A hat. This set is closely related to this maximal spectrum because it's easy to see that if we take a character, non-zero character, then its kernel is a maximal ideal. For the simple reason that the kernel of a linear functional is a codimensional one subspace. So it is maximal already in the set of all vector subspaces, of all proper vector subspaces of it, and moreover in the set of all proper ideals. So it's a maximal ideal. Thus we get a map from A hat from the character space to the maximal spectrum, which takes every character to its kernel. And it's easy to see that this map is always injective. Because if we take two characters with the same kernel, then they can differ only by a multiplicative constant. This is true for any two linear functionals. If you have two linear functionals on a vector space with the same kernel, then they are proportional. They can differ only by a multiplicative constant. So we want to show that this constant is 1. And to see this, we simply evaluate the identity. So the algebra is unital, so the characters are also unital. And so we see that lambda is 1. That is, chi1 equals chi2. So we get an embedding of the character space into the maximal spectrum. Sometimes, in many concrete examples, this embedding is actually a bijection. For example, if we take the algebra of polynomials in one variable, then it's a simple exercise to show that this is actually bijection. And again, this result extends to polynomials in several variables, and moreover, more generally to any finitely generated commutative algebra. This also follows from Hilbert's Nullstein sets. But we also have some counterexamples where this map is not bijective. For example, if you take any field extension of the complex numbers, for example, the field of rational functions in one variable, which properly contains the complex numbers, then it's easy to show that we have no characters at all. We have no, so a hat is empty. But the maximal spectrum is not empty because the zero ideal is the only ideal, the only proper ideal, so it's maximal ideal of our field. So in this case, our map is not a bijection. Now, our next goal will be to show that this map is a bijection provided that A is a Banach algebra, a commutative unital Banach algebra. And before proving this, let's prove the following lemma, which states that if A is a commutative unital Banach algebra, then all maximal ideals of A are closed. Well, why is it so? We take a maximal ideal I and observe that the closure of I is also an ideal, just by the continuity of the multiplication. So let's assume that I is not closed. So in this case, the closure of I is strictly bigger than I, but I was a maximal ideal. I was the maximal ideal, so that by the maximality of I, we deduce that the closure of I is equal to A. So in other words, I is dense in A. This means that I intersects any non-empty open set. Well, let's take this set of all invertibles in A. It is open. This was discussed in the previous lecture. So it is open. So this intersection is non-empty. But so this means that I contains invertibles, but an ideal which contains invertibles is equal to A. And this is a contradiction because I was assumed to be a proper ideal. Okay, so this shows that every maximal ideal of A is closed. And this, in turn, this implies that a commutative unital Banach algebra doesn't have dense proper ideals, because every proper ideal is contained in a maximal ideal, and the maximal ideal is not dense, it is closed. Okay, now we are ready to prove the following result, the following theorem, which states that if A is a commutative unital Banach algebra, then our map from the character space to the maximal spectrum, which takes every character to its kernel, is a bijection. Before proving this theorem, let's make a little but useful observation that if we take an arbitrary Banach algebra A and a closed two-sided ideal I, then the quotient of A modulo I is also a Banach algebra for the standard the quotient norm given by this formula. Well, indeed, it's a standard fact of functional analysis that the quotient of a Banach space modulo a closed subspace is also a Banach space, so it is complete. Also, it's an algebra because I is a two-sided ideal, and it's a very simple calculation to show that this quotient norm is submultiplicative. So the quotient of A modulo I is a Banach algebra. Now it's easy to prove our theorem. We already know that this map is injective. Now we have to show that it is surjective. So we take a maximal ideal, I, and look at the quotient of A modulo I. It's a Banach algebra, but at the same time, it's a field because I was a maximal ideal. So it's a Banach field. And let's now recall the Gelfand-Mazur theorem, which was discussed at the very end of the previous lecture, and which tells us in particular that a Banach field is actually the field of complex numbers. There is only one Banach field. So it is isomorphic to the complex numbers. Now we just take the quotient map of A onto the quotient of A modulo I, compose it with the isomorphism with the complex numbers, and obtain a character chi whose kernel is precisely I. And this shows that our map is surjective. So it is a bijection. As a corollary, we obtain the following useful invertibility criterion for elements in the commutative unital Banach algebra. So I claim that an element in A is invertible if and only if for every character chi away is non-zero. For every non-zero character chi away is non-zero. Well, the left-to-right implication is clear because chi is a character, it's a unital homomorphism, and it takes invertibles to invertibles. So chi away is non-zero. And to prove the right to left implication, let's suppose that A is not invertible. This implies that the proper ideal generated by A is sorry, the principal ideal generated by A is a proper ideal. The principal ideal, well, it's clear what that means. So it's a proper ideal because A is not invertible. So it is contained in a maximal ideal. But we already know that this maximal ideal is the kernel of a character, phi, and so K vanishes at A. Okay. From now on, let's adopt the following convention. So we will identify the character space with the maximal spectrum. This is quite reasonable because in some situations it's more convenient to look at elements of the set as characters. In some other situations, it's more convenient to interpret them as maximal ideals. So we just use this canonical identification between these two sets. Well, so far the set is just a set. And now our next goal is to topologize the set, to introduce a convenient topology and to make it into topological space. Before we do it, let's make a short digression to functional analysis, and let's recall some basic facts on the weak star topology. So the weak star topology can be defined on any norm, on the dual of any normed space. So we start with a normed space E, and for every element V, little v in E, we define a semi-norm on the dual space by the following simple formula. This is just the absolute value of f of v. And by definition, the weak star topology on the dual space E star is the locally convex topology generated by the family of all such semi-norms. So let's recall what this means. Such topologies, we have already met such topologies at the second lecture when we discussed the compact open topology. So explicitly, this topology can be described as follows. If we take an element of the dual space, a bounded linear functional, then the standard subbase of neighborhoods of F for the weak star topology consists of all sets of the following form. So the sets are indexed by an element V in E and by a positive epsilon. And this neighborhood consists of all functionals G satisfying this inequality. So the collection of all such neighborhoods is a subbase of neighborhoods of F. So they are finite intersections form a base of neighborhoods of F. Okay, here are some basic facts on the weak star topology. First of all, it's almost immediate that this topology is Hausdorff. Second, if we consider E star, the dual space, as a subset in the space of all complex valued functions on E, then and if we look at the standard subbase, we can easily see that the weak star topology is nothing but the restriction to E star, to the dual space of the standard product topology on C to the power E, on the space of all complex functions on E. In particular, this easily implies that a sequence Fn converges to F for the weak star topology, if and only if it converges pointwise. Another simple property, which is almost immediate from the definition, is that if we consider the evaluation maps from E star to the complex numbers, given by the following simple formula, then the weak star topology is nothing but the weakest topology on E star. That makes all these functionals continuous. A closely related property is that if we have a topological space X and a map from X to E star, where E star is equipped with the weak star topology, then this map is continuous if and only if all such compositions of phi with the evaluation functionals are continuous. In fact, this is almost equivalent to property 3. Another important property is related to the canonical embedding of E into the bidual. So let's recall that the canonical embedding of E into the bidual is given by the following formula. It takes every element little v to the respective evaluation functional epsilon v. So in the general case, we know from functional analysis that in the general case, this is an isometric embedding, but not necessarily it's surjective. Surjectivity means that E is reflexive. But for every norm space E, it turns out that the range, the image of this embedding, consists precisely of those functionals on E star, that is, of those elements of E double star, which are weakly star continuous, which are continuous for the weak star topology. Well, if we now have two norm spaces E and F, and a linear operator between their duals, which acts from F star to E star, then a useful fact is that such an operator is continuous, if and only if it has a predual, that is, if there exists a bounded linear operator between E and F, such that T is the dual of S. So in particular, the dual of any bounded linear operator is weakly star continuous. Is continuous for the weak star topologies. Well, and the final result, the final general fact we need about the weak star topology is the so-called Banach-Aloglu theorem, which says that the closed unit ball of the dual space is weakly star compact. It is compact for the weak star topology. By the way, let's recall that it's almost never compact for the norm topology. It is compact for the norm topology, even only if the space is finite dimensional. But it is always weakly star compact, which is quite useful. Okay, now we are ready to make the maximal spectrum into a topological space. So again, as before, we assume that A is a commutative unital Banach algebra. And we define the Gelfand topology on the maximal spectrum. So again, as usual, we identify the maximal spectrum with the character space. And we define the Gelfand topology to be the restriction to the character space of the weak star topology on A star. So at this point, let's recall that all characters are continuous. This was discussed at the previous lecture. So A hat is indeed a subset of A star, but A star carries the weak star topology. So we simply take the induced topology on A hat and we get the Gelfand topology. And by using this standard identification, we obtain a topology on the maximal spectrum. A useful property of the space is that it is compact and Hausdorff. Well, why is it so? First of all, since the dual space A star is Hausdorff for the weak star topology, this implies that A hat is also Hausdorff. Now, why is it compact? Well, let's also recall from the previous lecture that A hat is actually contained in the unit ball of A star. So the norm of a character is less than or equal to 1. So a hat is a subset of the unit ball. But the unit ball is weakly star compact by the Banach-Haloglu theorem. So now to prove that a hat is also compact, we simply need to show that a hat is closed in the unit ball. Well, why is it closed? Let's take any two elements, A and B, in A, and let's look at the following two maps from A star to the complex numbers. So the first map takes a functional f to the following number, f of ab minus f of a f of b, and the second one is just the evaluation of the identity. So the evaluation maps are continuous, so the second one is continuous, and the first one is a combination of evaluation maps. So this is the product of two evaluation maps. This is the evaluation map of f of ab. So they are continuous. The difference of two continuous functions is continuous. So we deduce that both maps are continuous. But on the other hand, what is a hat? A hat is the set of all unital characters, which means that a hat consists of those functionals from a star. Okay, so let's continue. So we see that a hat consists precisely of those functionals f in a star, which satisfy these two conditions. But since these maps are continuous for the weak star topology, this really implies that a hat is closed. So it's a closed subset of the unit ball, but the unit ball was weakly star compact by the Banach-Haloglu theorem. And so a hat is also compact because it's a closed subset of a compact space. Okay, now we are ready to introduce the Gelfand transform. Again, we assume that A is a commutative unit of Banach algebra. We take an element, little a, in our algebra, and we define the Gelfand transform of A to be the function a hat defined on the maximal spectrum of A and given by the following simple formula. So the definition looks like something trivial, but nevertheless, it turns out this is very useful. So every element of A determines a function on the maximal spectrum, that is, on the character space. So what can we say about this function? First of all, I claim that it is continuous. Well, indeed, if we look at this definition of a hat, we see that a hat is nothing but the restriction to the character space of the functional I of A, where I of A is the canonical image of A in the bidual in A double star. But let's recall once again that the range of the canonical embedding consists exactly of weakly star continuous functions. So I of A, our element I of A, is weakly star continuous, and a hat is just a restriction of this functional to a smaller set, to a hat, so it is weakly star continuous. Okay, so now we see that we actually obtain a map from A to the algebra of continuous functions on the maximal spectrum, which takes every element of our algebra to the functional little a hat. And this map is called the Gelfand transform of our algebra. The following theorem describes some fundamental properties of the Gelfand transform. First of all, I claim that the Gelfand transform is a unital homomorphism between A and the algebra of continuous functions on the maximal spectrum. And moreover, if the algebra is non-zero, then the norm of this homomorphism is exactly 1. Property 3 is that if we take the function little a hat, the Gelfand transform of an element little a, then its supremum norm is exactly the spectral radius of A. And the property 4 is that the spectrum of A is nothing but the range of its Gelfand transform of the function little a. And finally, I claim that the kernel of the Gelfand transform is exactly the intersection of all maximal ideals of A. Or equivalently, it is the set of all quasi-nilpotent elements. Well, why is it so? Well, part 1 is a trivial calculation, a little exercise for you to show that gamma is a unital homomorphism. Now, it will be more convenient to prove property 4, which states that the spectrum of A is the range of a hat. Why is it so? Well, a hat is a continuous function. So it's an element of the algebra of continuous functions. And we know that the element of this algebra, the spectrum of such an element is just the range of this function. So we have this equality. Now, property 4, which we want to prove, means precisely that gamma preserves the spectrum. So this is the spectrum of A, and this is the spectrum of a hat. So we want to show that gamma preserves the spectrum. But gamma is a unital homomorphism, and we discussed at the previous lecture that a unital algebra homomorphism preserves the spectrum if and only if it takes non-invertibles to non-invertibles. Well, let's prove that it takes non-invertibles to non-invertibles. We take a non-invertible element little a away, and let's call the invertibility criterion, which was proved some time ago. So by this criterion, it follows that we can always find a character of A such that chi vanishes at A. So this is 0. But this means that a hat, the Gelfand transform of A, the function a hat, vanishes at chi. And so it is not invertible in the algebra of all continuous functions. And that's it. So this shows that gamma takes non-invertibles to non-invertibles, and so it preserves the spectrum. Property 3, this equality, is immediate from property 4. We simply take the supremum of all elements of the absolute values of all elements in the set. So this supremum is equal to the spectral radius, and this supremum is equal to the supremum norm of a hat. So we get this equality. Property 2 is that the norm of gamma is 1. Well, indeed, on the one hand, we already know that the norm of a hat is the spectral radius, and the spectral radius is less than or equal to the norm of it. And so this inequality means that the norm of gamma is less than or equal to 1. But on the other hand, gamma is unital, so it takes the identity of A to the function which is identically 1, and this implies that the norm of gamma is exactly 1. So the final statement was about the kernel of the Gelfand transform. So just by the definition of the Gelfand transform, we see that the kernel of gamma is the intersection of the kernels of all characters. This is just the definition of the Gelfand transform. But on the other hand, because of our bijection between a hat and the maximal spectrum, we see that this is exactly the intersection of all maximal ideals of it. On the other hand, if we look once again at property 3, this is our property 3. So this function a hat is identically 0 if and only if the spectral radius of A is 0. That is, if and only if A is quasi-nilpotent. And so we deduce that the kernel of the Gelfand transform is the set of all quasi-nilpotents. And this completes the proof of our theorem. By the way, a short remark related to property 5. In the general case, that is, in the case where A is a unit or commutative algebra, that is not necessarily Banach algebra, there is a special name for the intersection of all maximal ideals. This intersection is called the Jacobson radical of A. In fact, the definition makes perfect sense for any ring, for any commutative ring with an identity. By the way, there is also a non-commutative analog of the Jacobson radical, but we will not need this notion. It's defined in a slightly different way. And we say that A is Jacobson semi-simple if the Jacobson radical is 0. So by looking at the Gelfand transform, we see that if A is Jacobson semi-simple commutative Banach algebra, then the Gelfand transform is an injection into the algebra of continuous functions. So in some sense, every commutative Jacobson semi-simple unital Banach algebra is a function algebra. Of course, this doesn't imply that its norm is equivalent to the supremum norm. In the general case, this is not true. But anyway, it is continuously embedded into the algebra of continuous functions on the maximal spectrum. A little but useful corollary of our theorem is as follows. If we look at the image of the Gelfand transform, it's a subalgebra in the algebra of continuous functions, then the subalgebra is spectrally invariant. Well, indeed, why is it so? If we take an element in this subalgebra, we write it in the form gamma of A, if it is invertible in the bigger algebra of all continuous functions, we recall that that gamma preserves the gamma takes non-invertibles to non-invertibles. This was here. This property was here. So it takes non-invertibles to non-invertibles. So this implies that A is actually invertible in A, but obviously this implies that gamma of A is invertible, an invertible element in the image of gamma. And this means exactly that the image of gamma is a spectrally invariant subalgebra. An important special case of this corollary is the famous Wiener's theorem. This result will be contained in the respective exercise sheet. Okay, let's now look at some examples. I have to switch to another presentation. So let's now look at some concrete examples of the maximal spectrum and the Gelfand transform. Just a moment. We'll be interested in subalgebras, and some subalgebras or the algebra of continuous functions on the compact Hausdorff topological space. So roughly what we want to prove is that for many subalgebras of C of X, its maximal spectrum can be identified topologically with X, and the Gelfand transform becomes just the inclusion map of our algebra into C of X. So in particular, for if A is exactly C of X, then the Gelfand spectrum is X, and the Gelfand transform is just the identity map of this algebra onto itself. Well, let's introduce some notation. We start with a compact Hausdorff topological space X. And for every point in this space, we consider the evaluation character of the algebra of continuous functions, which takes every function f to f of x. And the kernel of this character will be denoted by mx. We have the following useful lemma, which states that for every proper ideal I in C of x, we can always find a point in x such that I is contained in mx. That is, such that all functions in I vanish at the same point little x. In some sense, this lemma can be interpreted as a weak form of Nullstellensatz for C of x. Well, why is it so? Well, let's assume the converse. Suppose there is no such a point. That is, suppose for every point in X, there is a function fx in our ideal, which doesn't vanish at little x. Now, by continuity of this function, this function doesn't vanish and doesn't vanish in the neighborhood of x. So we choose a neighborhood u of x, ux, such that this function doesn't vanish on ux. By using the compactness of our space, we look at the collection of all such open sets ux, and we choose a finite subcover. So x can be represented as the following finite union. And we consider the following function, the sum of the absolute values, or the squares of the absolute values of fxi. This function sits in I because it can be equivalently written in the following form. I was an ideal. Each function fxi sits in the ideal, so the whole combination is in the same ideal. But on the other hand, by construction, this function is strictly positive everywhere, because fxi is strictly positive on the ith neighborhood, so f is strictly positive everywhere. In particular, it is invertible, because it is non-vanishing. And so we see that our ideal contains an invertible element. So this means that I is the whole algebra C of X, but this is a contradiction because I was assumed to be a proper ideal. And this completes the proof. In fact, we can say more. There is a more general result which describes all closed ideals in C of X. So this lemma essentially describes maximal ideals, and we can describe all closed ideals of C of X. This exercise will be in the respective exercise sheet. As a corollary, we see that if we consider a map which takes every point in X to the respective maximal ideal, Mx, or equivalently, we can consider it as a map to the character space, which takes X to the evaluation character epsilon X, then this map is a bijection. So it is surjective by this lemma. So clearly, if I was a maximal ideal, then I is equal to Mx by maximality. So by lemma, this map is surjective, and the injectivity follows from the standard fact that continuous functions separate the points. So if you have two different points, x and y, then we can always find a function which for f such that f of x is not equal to f of y. So it is a bijection between x and the maximal spectrum. Let's now introduce some notation. Suppose we have two compact Hausdorff topological spaces x and y, and a continuous map f from x to y. This map induces an algebra homomorphism, which will be denoted by f dot. It acts from C of y to C of x by the following simple formula. So we simply compose every continuous function of y with f, and we obtain a continuous function on x. Here are some simple properties of this map f dot. First of all, it's a unital algebra homomorphism, and moreover, its norm is exactly 1. Well, indeed, it's clear that it's an algebra homomorphism. And if we look at this formula, we see that, of course, the supremum of this function, phi composed with f taken over x, is less than or equal to the supremum of phi. And so the norm of this function is less than or equal to the norm of phi. And so the norm of f dot is less than or equal to 1. But since it is unital, we deduce that its norm is exactly 1. Again, except for the trivial case where our topological spaces are empty. But this is kind of trivial. If they are non-empty, then its norm is exactly 1. Also, it's clear that if we apply this construction to the identity map of x, we get the identity map of C of x. And finally, if we have two continuous maps, f from x to y and g from y to z, then we have the following equality. So gf dot is equal to the composition of f dot and g dot. In other words, these properties together imply that what we've just constructed is actually a contravariant functor on the category of compact topological spaces. We'll discuss this functor in detail a bit later. What is important now is that these properties together imply that if little f is a homeomorphism between x and y, then the respective homomorphism f dot is an isometric isomorphism between COY and COX. The fact that f dot is isometric follows from this formula. So its norm is 1. The norm of the inverse map is also 1. And this can happen only if f dot is an isometric isomorphism. Okay. Now we have the following result, which describes the maximal spectrum and the Gelfand transform for some nice subalgebras in COX. Specifically, we suppose that we have a subalgebra A in COX, which contains a function which is identically 1. And we suppose that A is a Banach algebra with respect to a norm which dominates the supremum norm. So I'd like to stress that we don't assume that the norm of A is equal to the supremum norm. Of course, this is also an important special case where A is a closed subalgebra of COX with the supremum norm. But in the general case, we only assume that the norm on A dominates the supremum norm. So a typical example to keep in mind is the algebra of continuously differentiable functions on the interval 0, 1. So it is continuously embedded into the algebra of continuous functions, but its norm is strictly stronger than the uniform norm. The second assumption, we assume that A separates the points of X. And finally, we assume that for every character of A, there is a point in X such that chi is the evaluation character. So in other words, property 3 means that all characters of A are the evaluation characters at points of X. In this case, if these properties are satisfied, I claim that the map epsilon from X to the character space of A, which takes every X to the respective evaluation character, is a homeomorphism between X and A hat. That is, between X and the maximal spectrum. And moreover, the final diagram commutes. So this is A. We have the Gelfand transform of A, which acts to the algebra of continuous functions on the maximal spectrum. We have the inclusion map of A into COX. And also we have an isometric isomorphism epsilon dot between these two algebras of continuous functions, which is induced by epsilon. So this diagram commutes. So in other words, this means that if we identify X with the maximal spectrum by means of this map, the Gelfand transform becomes just the inclusion map of A into COX. Well, why is it so? First of all, if we combine properties 2 and 3, we see that epsilon is a bijection. This is clear. Property 3 means that epsilon is surjective, and property 2 is equivalent to the injectivity of epsilon. So epsilon is a bijection. We want to show that it is continuous. Why is it continuous? Well, epsilon acts from X to A hat, and a hat is a subset of A star, where A star is equipped with a weak star topology. And let's recall, well, I'll not show you the previous presentation. I just draw a picture here. So epsilon can be looked at as a map from X to A star. where A star is equipped with the weak star topology. And by the property of one of the main properties of the weak star topology is that this map is continuous, if and only if the compositions with the evaluation maps are continuous. All such compositions are continuous. Well, we look at epsilon of x evaluated at A, but what this? This is just A of x. So in other words, this is just our function A, which is continuous just by assumption. A was a sub-algebra in the algebra of continuous functions. So it is continuous, and by this property of the weak star topology, we deduce that epsilon is continuous. As a result, we deduce that epsilon is a continuous bijection between x and A hat. But x and A hat are compact Hausdorff topological spaces, and the continuous bijection between such spaces is necessarily a homeomorphism. So epsilon is a homeomorphism. Finally, we have to show that the diagram commutes, and this is an explicit calculation. So we take an element A in here, we apply gamma, then we apply epsilon dot, and then we get a function on x, and we evaluate this function under little x. So what's this? Well, by the definition of epsilon dot, this is gamma of A evaluated at epsilon x. But now by the definition of the Griffin transform, this is epsilon x evaluated at A, which is just A of x. So we deduce that the composition of this arrow and this arrow is just the inclusion map. And this completes the proof. So this theorem is quite useful because it applies to many concrete examples of commutative Banach algebras. So if you want to describe explicitly the maximal spectrum and the Griffin transform for some Banach algebra, it's useful to look at whether or not our algebra satisfies the conditions of this theorem. Because if it satisfies, then we see that the Griffin transform is just the inclusion map. In particular, as a special case, we see that if A is the whole algebra of continuous functions on X, then gamma is an isometric isomorphism between A and C of X, and the inverse map is nothing but epsilon dot. So in this diagram, this arrow becomes the identity map, and so since epsilon dot was an isomorphism, we deduce that gamma is also an isomorphism, and the inverse of gamma is epsilon dot. Okay, we still have some time. In conclusion, let's discuss some useful functorial properties of the Griffin transform. So let's look at two categories. The first category will be denoted like this. It will be denoted by comp. The objects of this category are compact Hausdorff topological spaces, and the morphisms are just continuous maps. And the second category will be denoted by cuba. The objects are commutative unital Banach algebras, which explains the name, and the morphisms are continuous unital homomorphisms. So we have two categories, and we have two contravariant functors between these categories. The first one was already discussed some time ago. It will be denoted by C, and it takes every compact Hausdorff space X to the algebra C of X, which is a commutative unital Banach algebra. And if we have a morphism of compact spaces, that is just a continuous map from X to Y, then our functor C takes this map to the homomorphism F dot, given by this formula. The second functor will be denoted by max. It acts in the opposite direction, that is from the category cuba of commutative unital Banach algebras to the category of compact spaces, and it takes every commutative unital Banach algebra A to its maximal spectrum, or equivalently to its character space. If we now have a morphism between such algebras A and B, then our functor takes this morphism to the map denoted by phi star, which is given by the following formula. So here we interpret maximal ideals as characters. So it takes every character of B, every character chi of B, to chi composed with phi, which is obviously a character of I. Why is it continuous? It is continuous because this map is nothing but the restriction of the dual map of phi. If we take the dual of phi, it acts from B star to A star. And we already know that the dual to phi is weakly star continuous. So when we restrict to the character spaces, we get a continuous map between the character spaces. Okay, so this is the functor max. We have two contravariant functors. And the following simple exercise describes an important relation between these functors. First of all, we already know that for every compact Hausdorff topological space, we have a homomorphism between X and the maximal spectrum of C of X. This is just the homomorphism from the previous theorem. But we can say more. All these homomorphisms considered for all compact Hausdorff topological spaces are compatible in the sense that they form a natural isomorphism between the identity functor on compact Hausdorff topological spaces and the composition of max and C. So these two functors are naturally isomorphic. The second exercise is that if we now look at the Gelfand transform and look at the Gelfand transform of every commutative unital Banach algebra, then this is a natural transformation from the identity functor on the category of commutative unital Banach algebras to the composition of C and max. At this point, of course, I don't say that this is a natural isomorphism. This is just a natural transformation, which means that, well, let me recall what that means. This means that whenever we have a Banach algebra homomorphism from A to B, so A and B are commutative unital Banach algebras, we can also consider the respective homomorphism from the algebra of continuous functions on max of A to the algebra of continuous functions on max of B, which is defined just by composing two constructions. First, this map phi induces a map from max of B to max of A, and we apply C. C is also a contravariant functor, and we get a homomorphism from this algebra to this algebra. Well, we have also the Gelfand transform here, the Gelfand transform here, and the fact that gamma is a natural transformation means precisely that this diagram commutes for every homomorphism phi. Well, the commutativity of the diagram is a simple exercise. So it's a natural transformation. And finally, I claim, this is also quite straightforward, that we have actually a bijection, a one-to-one correspondence between the set of all homomorphisms from A to C of X, where A is a commutative unital Banach algebra, X is a compact space. So there is a one-to-one correspondence between such homomorphisms and continuous maps from X to the maximal spectrum of A. And this bijection is very explicit. If we have a homomorphism phi from A to C of X, then we can do the following. First, we take the homomorphism epsilon x, which acts from X to this maximal spectrum of C of X, and phi star takes the maximal spectrum of C of X to the maximal spectrum of A. We compose these two maps, we get a map from X to the spectrum of A. And the inverse construction is also quite easy. We start with a map here from X to the maximal spectrum. Then we can do the following. First, we take the Gelfand transform of A from A to the algebra of continuous functions on the maximal spectrum, and we compose it with the homomorphism F dot induced by F. And this composition is a unital homomorphism from A to C of X. And it's a little straightforward calculation to show that these two constructions are inverses of each other. So we have a bijection between these two sets. So to make this picture more compatible with the standard notions of category theory, let's replace the category of compact spaces by the opposite category, which has the same objects and the arrows look in the opposite direction. And we deduce that we have a bijection between this home set and this one. And in other words, because these bijection are natural, we deduce that we obtain an adjoint pair of functors. So the functor or the maximal spectrum is left adjoint to the functor C. Okay, so that's all for today. At the next lecture, we first of all will discuss a non-unital version of Gelfand's theory. That is, we discuss the non-unital version of the maximal spectrum and of the Gelfand transform. Well, maybe this is probably quite exotic from an algebraist's point of view. So algebraists normally work with unital rings and unital algebras, but we already know that in our theory, in commutative harmonic analysis, there are many important non-unital algebras. First of all, the algebra of L1 of G, where G is a non-discrete locally compact group. So to work with non-unital algebras, we have to modify the maximal spectrum and the Gelfand transform to the non-unital case. And after that, we specialize to C-star algebras. And after proving some results about spectra of elements of C-star algebras, we'll prove one of the fundamental results in the C-star algebra theory, namely the commutative Gelfand-Naimark theorem, which states that for any commutative unital C-star algebra, well, actually not necessarily unital, for every commutative C-star algebra, the Gelfand transform is an isometric star isomorphism, which is quite important. Okay, thank you. That's all for today.
Спасибо. До свидания.
Спасибо. До свидания.